Welcome to Calculus. Today we will investigate differentiating trigonometric functions, focusing on applying the 6 derivative rules to functions involving sine, cosine, tangent, cotangent, cosecant, and secant ratios. We'll take a look at a total of 5 examples, beginning with a simple one and then building up to more complicated derivatives as we go. So let's take a look at our first trigonometric function. We are looking to find the first derivative of y. And we're told our function is y equals x minus sine of x. So I see that I need to apply my difference rule for differentiation because I got x minus sine of x. So as I start to record the derivative of y, I can begin with that derivative of x. Remember, that's my linear term, which has the derivative of 1. And then I'm going to also find the derivative of the difference of sine of x. So what we need really is our rule for what is the derivative of the sine of x. So here in our chart, that's our first entry. So if I've got that function, its derivative, so d dx sine of x is going to be cosine of x. So there's a relationship between the sine function and really the slopes of the tangent lines to the sine function are described by cosine. So that is really quick to differentiate. All I got to do is record cosine x, and that is my derivative. The derivative of y is 1 minus cosine of x. So a very simple example to begin, applying the difference rule and then also the trigonometric sine rule. Let's see for a more complicated function. Now when we have 2 trigonometric functions. So here are y equals tangent of x plus cosine of x. And again, I want to find the derivative y. So what I'm looking for now are derivatives for 2 others, for tangent of x and cosine of x. So second in our table here is the function cosine x. So its derivative, d dx cosine x. And understandably so, it's related to sine of x. So the slopes of the tangent lines to the cosine function equal, the main difference is that this is equal to negative sine of x. We also need to catch the derivative of tangent of x. So let's go ahead and fill that in while we're here on our table. So if I've got tangent of x, the slopes of the tangent lines to the tangent function will be equal to secant squared of x. So we see here there's a relationship between the slopes of the tangent lines to the tangent function and the secant of x function, secant squared of x, in fact. Well, that gives me enough to write the derivative to this function y. Y prime, or the first derivative of the y function, are going to be the derivative of tangent of x, which we just saw was the secant squared of x. And then plus the derivative of cosine of x, which is given as negative or minus sine of x. And really we had 2 trig functions here, but the derivative of that one, again, since it was set up as a sum or a difference, is pretty straightforward. Derivative of tangent x plus cosine x is secant squared x minus sine of x. Well, let's take a look at a product. So here I've got the cotangent of x times the tangent of x. And again, I need another derivative rule because I don't know the derivative of cotangent yet. So here I've got my table filled in with those first 3 that we've already used. What we want to find is now, what is the derivative of cotangent of x? So that's the next entry here in our table. So if I got cotangent x, derivative d dx cotangent of x is going to be negative cosecant squared of x. So you can see that pattern that we established at first between the derivatives of sine and cosine, where they're opposite of each other. So derivative of sine is cosine, but derivative of cosine is negative sine. We have that same relationship appearing here between tangent and cotangent. And really it's a relationship between tangent, cotangent, secant, cosecant. But I do have the difference in the two signs. So derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. So we want to apply those, but notice this is a product. And so I need to mind my product rule. So remember what product rule says. If I've got a big function f of x, which is equal to the product of two smaller functions, so f of x, small f of x, times small g of x, the derivative of big F of x is going to be equal to small f of x times the derivative of g of x plus, let's get the right operation there, plus the original small g of x times the derivative of small f of x. So we're going to follow that same pattern, but we need to use our new rules here. So what I'll identify as my small f of x is cotangent x. So I want to find its derivative so I can plug it into the product rule. So the derivative of small f of x from my table I see is going to be negative cosecant squared of x. Similarly, I want to identify small g of x. That's my second factor in this product, is going to be tangent x. So the derivative of small g of x is going to be secant squared of x, and that's positive. So we just want to set up then. So for us, we'll call this y prime, the first derivative of our function. And we'll follow our rule here. So it's f of x, which we saw as cotangent x, times the derivative of g of x, which is secant squared of x, plus the original g of x, which is tangent of x, times the derivative of small f of x, which we labeled as negative cosecant squared of x. Now we could box that and say that's that. Or we could try to reduce that down and see really what is that when I simplify these trig expressions. So we'll box it, but let's see if we can find a more simplified form. So one thing we got to remember is that cotangent, secant, tangent, and cosecant are all definable in terms of sine and cosine. So I'm just going to start rewriting stuff. Cotangent is equivalent to cosine over sine of x. I'm going to write it in a simplified form there. And then secant squared x is really, if I think secant, that's the inverse of cosine. So it's 1 over cosine. And then the squared part is that I would write it twice. Now, if we just want to focus on this first product, so cotangent times secant squared, I can see that at least one of the cosines is going to cancel, and that would reduce to the fraction 1 over sine times cosine. Well, let's see if that does anything for us. So I'm going to look at this second product group. So tangent, recall, can be defined as sine over cosine. And then negative cosecant squared x, that negative's on the outside. So I'll put it there once. Let's just put it as a -1. And then cosecant could be defined as 1 over sine. And since it's squared, I'll put 2 factors. So again, I see a cancellation, at least one sign goes, and what we're left with here is minus from the negative 1 over, if I put sine first, sine cosine. So that looks like that equals 0. So let's just think in terms of the original. Is that possible? Is it possible for the derivative of this function to just reduce to 0? Well, I'll go back to the original function, cotangent times tangent, and just use those same rules. Cotangent is cosine over sine. Tangent is sine over cosine. Well, I got two cancellation pairs there. Cosines cancel, sines cancel. So this is really equivalent to 1 times 1 or 1. So if I simplify the original, reduces down to just a value of 1, it's a constant. And if I took the derivative of a constant, according to my rules, the derivative of a constant is 0. So it checks out in terms of the original function. So we could either write it as that kind of sum of two different products, or if we reduced it down, we could say, hey, that should have the value of 0. So we've looked at 3 of our examples taking derivatives of trigonometric functions. We'll take a look at 2 more examples, but let me let you go practice your own differentiation of trig functions. See you soon.